What if the most powerful fuel station in the entire solar system has been sitting right above your head every single night, hidden in frozen darkness for over 1 billion years, and nobody knew it was there until right now? That is not a science fiction premise. That is exactly what scientists have confirmed about our moon, and the implications of this discovery are so massive that they are going to completely rewrite how humanity travels through space forever. For centuries, people looked at the moon and saw a dead, dry, barren rock. Even the greatest scientific minds on Earth believed it had no water at all. When NASA's Apollo astronauts brought back samples from the lunar surface in the late 1960s and early 1970s, those rocks appeared completely dry. The moon was officially declared a waterless world, and that conclusion was accepted as fact for decades. But science has a beautiful habit of proving itself wrong, and the moon just handed us one of the biggest surprises in the history of space exploration. Water is up there, enormous amounts of it, and not just tiny traces either. NASA estimates suggest there could be anywhere from 600 million to 1 billion metric tons of water ice hiding on the moon right now. Let that number sink in for a moment. 1 billion metric tons of frozen water, sitting in craters so cold and so dark that sunlight has never touched them, some of them remaining in complete shadow for billions of years. This is not a small discovery. This might be the single most important resource find in the history of space exploration, and the reason why has everything to do with the chemistry of rocket fuel. Here's the thing most people do not realize about space travel. The single biggest problem with getting anywhere beyond Earth is fuel. When a rocket launches from the ground, it burns through an absolutely staggering amount of propellant just to escape gravity. A significant portion of a spacecraft's total weight on launch day is nothing but fuel. And if you want to go anywhere further than low Earth orbit, like the Moon or Mars or beyond, you need even more fuel waiting for you at the destination, or you need to carry all of it with you from the start. Carrying that much propellant from Earth is extraordinarily expensive. Launching just 1 single kilogram of payload to the Moon costs somewhere between $20,000 and $50,000 depending on the rocket system being used. So if you need 10 tons of propellant for a deep space mission, you are looking at paying somewhere between $200 million and $500 million just for the fuel alone. That is before you even start thinking about the spacecraft, the crew, or the mission itself. This is exactly why lunar ice changes everything. Water, which is made up of hydrogen and oxygen, can be split apart through a process called electrolysis. When you run an electrical current through water, it breaks the molecules down into their 2 component gases. Those 2 gases, hydrogen and oxygen, happen to be the exact same chemicals used to make liquid rocket propellant. A single ton of water can yield approximately 890 kilograms of oxygen and 110 kilograms of hydrogen. That is enough to refuel a lunar ascent vehicle or provide life support for a crew of 4 for several months. And the moon has potentially 1 billion metric tons of this stuff just sitting there, locked in the soil, waiting to be used. Think about what this means in practical terms. Right now, every space mission that wants to go anywhere beyond Earth orbit has to bring all of its fuel from home. It is like driving cross-country, but having to carry every drop of gasoline you will ever need in the back of your car from the moment you leave your driveway. There are no gas stations along the route. You either bring enough or the mission fails, but if the moon becomes a fuel production hub, suddenly that entire equation changes. Spacecraft could launch from Earth with just enough fuel to reach the moon, refuel there using propellant produced from lunar ice, and then continue onward to Mars or anywhere else in the solar system with a full tank. The moon stops being just a destination and starts being a launch pad. Scientists and engineers have started calling this concept exactly what it sounds like, a space gas station. George Sowers, a mechanical engineer at the Colorado School of Mines who has spent years studying the economics of space resources, put it simply and powerfully. He said that water is the oil of space. And just like oil transformed transportation and industry on Earth over the last 2 centuries, lunar water ice has the potential to transform space travel in the century ahead. Now, the question that scientists spent decades arguing about is where all this ice actually came from in the first place. For a long time, the prevailing theory was that the moon's water arrived in a single dramatic event, perhaps a massive comet impact or a concentrated shower of icy asteroids during a period called the Late Heavy Bombardment, which happened roughly 4.1 to 3.8 billion years ago. But a new wave of research has completely dismantled that single event theory. The real answer is far more fascinating. According to a landmark study published in Nature Astronomy and led by planetary scientist Oded Aharonson from the Weizmann Institute of Science, the moon's ice did not come from one big delivery. It built up slowly, continuously over billions of years, through multiple overlapping processes happening at the same time. Researchers used temperature, data from NASA's Lunar Reconnaissance Orbiter, and ran sophisticated computer simulations tracking how craters have changed across billions of years of lunar history. What they found was striking. Older craters consistently contain more ice than younger ones. That pattern only makes sense if water has been arriving and accumulating gradually over an enormous span of time, rather than appearing all at once from a single ancient catastrophe. So where did all the water come from? The answer is that it came from everywhere. Comets and asteroids, which naturally carry ice in their composition, have been slamming into the moon since the earliest days of the solar system. Each impact delivered a small contribution of water to the lunar surface. Ancient volcanic activity also played a role. Around 2 to 4 billion years ago, the moon was volcanically active, and those eruptions released water vapor from deep inside the lunar interior. Some of that vapor drifted toward the poles and froze in the cold, shadowed craters. And then there is a third process that is still happening right now, today, even as you watch this video. The sun constantly emits a stream of charged particles called the solar wind. When those hydrogen particles strike the lunar surface, they can chemically interact with oxygen in the lunar soil to form tiny amounts of water molecules on the spot. Paul Hayne, a planetary scientist at the University of Colorado Boulder's Laboratory for Atmospheric and Space Physics, explained it clearly. Through the solar wind, a constant stream of hydrogen bombards the moon, and some of that hydrogen can be converted to water on the lunar surface. The moon has been quietly making its own water for billions of years. All of these processes together, asteroid and comet impacts, ancient volcanism, and continuous solar wind chemistry, created the ice deposits that are sitting on the moon today. And crucially, scientists now believe the moon has been accumulating water more or less continuously for somewhere between 3 and 3.5 billion years. That is a timeline almost too long for the human brain to genuinely process. While life was just beginning to get complicated on Earth, the moon was slowly banking its water reserves in frozen underground vaults. Those vaults are located in what scientists call permanently shadowed regions. These are craters near the lunar north and south poles, where the geometry of the terrain means sunlight never reaches the floor. Because the moon has almost no tilt to its axis, the bottoms of these polar craters sit in eternal darkness. The temperatures there drop to around minus 410 degrees Fahrenheit, making them some of the coldest naturally occurring places in the entire solar system. Colder than Pluto. In that extreme cold, any water molecules that find their way in simply freeze and stay frozen essentially forever, because there is no warmth and no atmosphere to disturb them. NASA's Lunar Reconnaissance Orbiter has been mapping these regions in remarkable detail. One crater in particular, Shackleton, located right at the lunar South Pole, has become a focal point for scientists. Analysis of radar reflections from Shackleton suggests that up to 22% of the material inside it could be made of ice. The crater's rim sits in almost continuous sunlight, which is ideal for generating solar power, while its floor is in permanent darkness, which is ideal for preserving ice. It is almost as if nature designed the perfect location for a lunar base on purpose. Other craters like Cabeus and Haworth have also shown extremely high concentrations of water ice in their soil. In 2009, NASA's L-Cross mission deliberately crashed a rocket stage into Cabeus crater and then flew a spacecraft through the resulting debris plume to analyze what came out. The results confirmed that ice made up about 5.6% of the ejected material by mass. More recent studies using NASA's Lunar Reconnaissance Orbiter show ice deposits extending even further from the poles than previously thought, reaching at least 77 degrees south latitude, with roughly 5 liters of ice hiding in every square meter of the top meter of lunar soil in those regions. These are not fleeting surface frost patches. These are substantial deposits, capable of supporting long-term operations. Extracting that ice is not as simple as just scooping up snow, but the technology to do it is real and it already exists in prototype form. The basic plan is to use automated mining systems that heat the lunar soil above 230 degrees Celsius, hot enough to sublimate the frozen water directly into vapor without needing to melt it first through liquid form. That vapor is then captured and stored. Once you have liquid water, you run electrolysis to split it into hydrogen and oxygen gases, then cool those gases down until they become liquid propellant ready for use. The whole process requires electrical power, which can be generated using solar panels placed on the sunlit crater rims just above the shadowed ice deposits. The engineering is complex, but none of it requires technology that does not currently exist. The economic argument for doing this is overwhelming. Right now, getting propellant to deep space is one of the most expensive problems in all of human spaceflight. If lunar ice can be used to manufacture rocket fuel on the moon, mission planners estimate it could reduce the cost of deep space exploration by as much as 90%. That is not a small efficiency gain. That is a complete restructuring of what is possible. Missions to Mars that currently seem financially out of reach suddenly become viable. Permanent outposts throughout the solar system become conceivable. The moon as a refueling hub makes the entire rest of the solar system dramatically more accessible. Multiple space agencies and private companies have recognized this reality, and the race to access lunar ice is genuinely underway. NASA's Artemis program is focused specifically on returning astronauts to the lunar South Pole, precisely because that is where the ice is. China's Chang'e missions have been building toward the same goal. Private companies are developing concepts for autonomous ice mining robots. NASA has even sent instruments specifically designed to locate, map, and analyze lunar ice in greater detail than ever before, with more missions on the way. What makes all of this even more extraordinary is the timing. For billions of years, that ice sat there in the dark, undisturbed, preserved perfectly in one of the coldest places in the solar system. It survived asteroid impacts, solar flares, and billions of years of cosmic radiation. It waited through the entire span of complex life on Earth. It was there when the first humans looked up at the night sky and told stories about it. It was there when Galileo pointed a telescope at it in 1609. It was there when Apollo astronauts walked across its surface and came home believing it was completely dry. And now, right now, in this exact moment of human history, we have finally developed the science, the technology, and the ambition to find it, understand it, and use it. The moon kept it secret for over 1 billion years, but the secret is out now, and what comes next is nothing short of a complete transformation of what humanity can do in space. The gas station has been there the whole time. We are finally ready to open it.